This is the second presentation in the Power, Energy and Economy series. Today I wish to speak about the recommended method of carrying out an economic analysis of a medium-sized hydropower plant. And the figures I use are related to Pakistan. So to start with, I wish to bring out the fact that the conventional power appraisal, project appraisal, uses avoided cost concepts. Usually the proposed hydropower plant is compared with the steam turbine. This is unfair comparison since a base load thermal is compared with a hybrid. The hydro is a peaking plant and also provides off-peak energy. If you do this, it will lead to either overinvestment or it will lead to an unacceptable or uneconomic project, and it definitely will result in an improperly sized power plant. Therefore, there is need to come up with an approach which captures the impact that the proposed hydropower plant will have on the power system. And this is very important because otherwise you will have projects which do not add value to the system. Now, the recommended method, there are more than one. One would be to compare the hydropower investment with a thermal equivalent projects. The equivalence method, the so-called equivalence method, is based on the assignment of benefits to a hydropower plant based on avoided cost of thermal equivalent plants. I say plants because one plant does not capture the impact that the hydropower plant will have on the system. And why is that? Because the hydropower plant generates power which will be at the maximum during the peak runoff during, say, summer, and will be at the lowest output in winter. So the average output of a hydropower plant will vary from month to month. In fact, season to season will be a better comparison. It will be high in winters and it will be low it will be high in summers and it will be low in winters. This also means that the hydropower plant, the installed capacity is a poor guide to the avoided plants that would result as the hydropower plant is installed. Since the entire installed capacity is not available the whole year, therefore we go to a concept called firm installed capacity. The firm installed capacity is what the hydropower plant can generate for 4 peak hours 90% of the time. When I say peak hours, it is because the hydropower plant is usually designed to cater to the peak periods, to the 4 hour peak periods or 4.5 hour peak periods, and therefore whatever capacity is available 90% of time during these 4 hours throughout the year would be the firm capacity. That would be the capacity that will be replaced. You will not add that many megawatts of a thermal gas peaking turbine in the system because the hydropower plant has been installed. So the contribution of the other contribution of the hydropower plant is what is provided off peak. Since the off peak you do not avoid any capacity, there are no capacity benefits for off peak. But the off peak does avoid equivalent thermal energy, and the avoided fuel cost is the added benefits. So in short, the benefits of a hydropower plant are the firm capacity, the capacity that the plant can deliver 4 hours each day for 90% of time, say for 330 days a year, the peak energy and off-peak energy. Now I differentiate between peak and off-peak energy because there is a spread between the cost of peak and off-peak energy. Peak energy is usually much more expensive than off-peak energy, both because of the fuels used, but even if the same fuel is used, there's a difference in the efficiency of the machines we are comparing. The peak turbine is a much less efficient machine than a base load machine. Therefore, peak energy will always have a higher value than off-peak energy. And if the hydropower plant avoids generation of peak and off-peak energy, these should be treated separately, peak and off-peak energy. Now, the thermal equivalent of a hydropower plant therefore is an open cycle gas turbine equal to the firm capacity of the hydropower plant. Firm capacity, remember, is the one we have defined before, that is available 4 hours a year, 90% of time, or say 330 days a year. And this firm capacity avoids a equivalent thermal open cycle gas turbine. Whereas its fuel and variable O&M is the peak energy price. And remember, we want to differentiate between peak and off-peak price, and we have already gone into why is that. Now the other part of the output of the hydropower plant is energy contribution split into peak and off-peak components. The equivalent approach is a fair measure of the economic worth of a hydropower plant. Now you must remember that we are not comparing a hydropower plant with a single thermal plant. We are in fact comparing the hydropower plant to a open cycle gas turbine equivalent to the firm capacity, and we are avoiding the output of a base load plant off peak, and we differentiate between energy contributions of the hydropower plant by peak and off peak, as both have different cost and benefit figures. Now, the thermal equivalence approach is, as I already said, is a fair estimate of the economic worth of a hydropower plant, but it does not capture fully the entire impact of the addition of the hydropower plant, which is why it is recommended that you use what is called the LRMC approach. The LRMC is the long run marginal cost of the system at various voltage levels. I say various voltage levels, and I want to introduce another element here, because the hydropower plant usually, if it is a medium size, small size plant, does not contribute energy at the generation level. It avoids EHV transmission, 500 to 20 kV transmission, and will serve energy at 132 kV level. When you do that, then you are in fact avoiding needed transmission costs in 500 and 220 kV, and which is a benefit. So the long run marginal cost by voltage levels captures both the impact of peak, off peak impact of the plant, the variation of the plant over seasons, over months, and also the geographic location of the plant. So there are, of course, estimates available of a long run marginal cost. These vary with changes in fuel prices, and also with the future transmission and distribution expansion plans. But in summary, I would say that the long run marginal cost captures the essence of adding the hydropower plant into the system. It fully captures the benefits. The thermal equivalence approach is a fair estimate of the economic worth of a hydropower plant, and I repeat, we do not compare the hydropower plant with a single thermal plant, but we compare the output of the hydropower plant to three different outputs. The firm capacity of the hydropower plant, that is the 4-hour peak availability over 90% of time, is compared to the avoided cost of a equivalent gas turbine, open cycle gas turbine. The peak energy is the avoided cost of that gas turbine, and the off peak energy is the avoided cost of a base load mid thermal power plant placed in the merit order somewhere in between. But the recommended approach, I repeat, is the long run marginal cost approach, because it fully captures the impact of adding the power plant to the system. Thank you very much.